In this video, we introduce our work DeCo, Decomposition, and Reconstruction for compositional temporal grounding via Coarse-to-Fine contrastive ranking. This work is done by Lijin Yang, Xuan Kong, Huan Keng Yang, Wadim Kel, Yoichi Soto, and Norimasa Kobori from the University of Tokyo and woven by Toyota. We specifically focus on the temporal grounding task. In this task, given a sentence as the description, the goal is to localize the temporal start and end of this sentence from an untrimmed video. For example, given the query, a smiling man posing while the camera flashes in front of him, our task is to identify when this activity starts and ends in this video. For improving practicability, it is necessary that the temporal grounding can also be done on novel semantics. One characteristic of human natural language is that novel semantics can be described by combining known words in novel ways. By leveraging this characteristic, we aim at the task of compositional temporal grounding, for developing a model that can generalize to novel semantics. For compositional temporal grounding, it is necessary that the model has a primitive understanding of different elements in a sentence and connect it to the video part. However, we do not have a dense annotation of each component in the sentence. For example, the current form of annotation does not provide where exactly the reporter in blue is, or when the people trim the dog's nail. To address the pre-mentioned challenges, we propose a method based on decomposition and reconstruction. Here is an overview of our method. We will introduce each part in detail in the following slides. The first part of our method is a coarse-to-fine sentence decomposition. We first conduct part of speech tagging, getting the tag of each sentence. We then use a set of prompt templates and construct new sentences. To build positive samples, we use entities from the corresponding sentence to fill the prompt. To build negative samples, we use an entity from another sentence. The sentence building is repeated for k times. Including the original query, we acquire 3k plus 1 sentences as input. With the new sentences as input, we use a vision text transformer to predict the corresponding temporal boundary of each sentence input. The predicted temporal boundaries are also referred to as proposals. As mentioned in the sentence decomposition part, given paired video A, its corresponding sentence description A and the mismatched sentence B, we can build 3 subsentence P, C, and O. Naturally, we then get their ranking relation regards of video A, which is the correspondence of video A and query A is larger than subsentence P, and further larger than the negative sample C and then larger than the negative sample O. To measure whether the proposals are good enough, we use the masked-based self-supervised method. We assume that if a proposal can better reconstruct the input query sentence, then it is a good proposal. Otherwise, like in this example, is a bad proposal. Therefore, given the ranking relations, the masked language reconstruction loss using proposals generated by query A should be smaller than the loss of using subsentence P proposals. Hereby, we build the ranking loss and the reconstruction loss. We conduct our experiments on 2 public datasets, Charade CG and ActivityNet CG. These 2 datasets are both split into 3 sets. The training set is the known data for training. The test trivial set is the set that the descriptions used for testing existed in the training set. In the novel composition set, the scene description used for testing does not exist in training. We consider 5 types of compositions, namely verb noun, adjective noun, preposition noun, noun, and verb adverb. To the right shows 15 common novel compositions of each type in the Charades dataset. We first show the results on the ActivityNet CG dataset. We compare with multiple previous methods, and can outperform all of them. The work visa in the last row uses additional detector knowledge as input, so we do not directly compare with this method, but show its results here for reference. On this page, we show the results on the Charade CG dataset. Similarly, our method can outperform all of the previous works. In this ablation study, we examine the effectiveness of each component added to our contrastive ranking. It is clear that each of these relations can positively benefit the overall performance. From the comparison between B and C, it can be also seen that by simply introducing the composition subsentences, without contrastive ranking, we cannot guarantee better performance. On the other hand, comparing C and D, introducing the composition sub-sentences, along with the concept of contrastive ranking increase the performance. This hints towards our proposed concept of having advantages for visual temporal grounding. Here we show some qualitative examples from the Charade CG dataset. In this example, we can see that with ranking, our method with ranking can perform significantly better than the baseline. In this example, our method also shows much better performance compared with the baseline method. Thank you very much for your listening. If you have further questions, please come to our poster or drop messages in the chat box.